Good day. My name is Talitha Washington, and I am the director of the Atlanta University Center Data Science Initiative. And before I introduce our speaker, I'm just going to share a couple updates about first about the initiative and what's happening around the data land in the AUC. So the Atlanta University Center Data Science Initiative works collaboratively with Clark Atlanta University, Morehouse School of Medicine, Morehouse College, Spelman College, and the AUC Woodruff Library. We are also funded by the United Health Group. And first I want to do a quick thanks to our sponsors, including the United Health Group, who is our founding sponsor, and also Coca-Cola and SAP, who are also our sponsors. And we have just been recently joined by Truist. So we're really thankful to these sponsors in supporting our work and working collaboratively with us to build data science opportunities. Just a quick recap. A few weeks ago, back in the month of September, we had our inaugural virtual student data science symposium, and it was really successful. We enjoyed lightning talks by undergraduate students on their data science research or internships experiences. We also have an HBCU data science resume book made available to our exhibitors and also our sponsors. If you're interested, let us know. And in this book, it features resumes of 76 students from 18 different HBCUs who are interested in data science careers or graduate study. So we really had a good time with this virtual student data science symposium and look forward to holding this next year in September. And kudos, job well done to all the students who participated. Just a reminder for the folks here in the AUC, if you'd like to use the virtual computer lab for data science research or teaching or project work, both AUC students, faculty, staff, administrators, please let us know. We would like to extend this as a resource to you. And this is funded by Coca-Cola and SAP in collaboration with the library. The AUC Data Science Club is well underway, having activities. So this is all call to all AUC students, undergraduate students and graduate students to come join in the fun of the Data Science Club. The next meeting is October 14th. They're going to have an R workshop taught by Brian Briones of the Woodruff Library, and they have other exciting upcoming opportunities. So please, if you have students who you think would be interested in Data Science Club, please send them this information. And in a moment, we'll put a link to where students can sign up to get notifications about the club in the chat. So without further ado, our speaker today is Dr. Talon Johnson. He is going to talk with us about a new approach for faster acquisition and deblurring of imaging data in magnetic resonance. So Talon, he was a math major here at Morehouse College. And then after graduating, he went to the University of Texas at Arlington, where he earned his PhD in mathematics. Most recently, he is now a postdoctoral scholar through the prestigious NSF Award, the NSF MPS Ascend program. So he has an NSF funded postdoctoral scholar where he's going to begin his work in January. And part of that work will be here at the Atlanta University Center. So if, folks who are out there, if you can think of ways to engage with him to extend his work, or perhaps your work could be leveraged in your research or work, please reach out. We look forward to hearing about his presentation today. And we also look forward to spending more time with him in the upcoming year. So without further ado, I would like to introduce our speaker, Dr. Talon Johnson. Dr. Johnson?
Hello, Dr. Watson. Hello, everyone, all attendees and stuff. I'm glad to be here today to share you with some of my research and some of my experience here at University of Texas at Arlington. So I will start off with the presentation. I'll share my screen to share the presentation. All right. So today I'd like to talk to you all about a new approach, the research I've been doing during my PhD, in which Dr. Washington has already set the title, a new approach for faster acquisition and deblurring of imaging data in magnetic resonance. But I would like to first, before I start, I'd like to talk about my journey to the PhD program, coming from Morehouse all the way to the University of Texas at Arlington and graduating. So when I went to going to Morehouse, I was presented with a lot of opportunities. And I think the Morehouse math department, Dr. Dwayne Cooper, especially Dr. Dwayne Cooper, for trying to get a lot of the students in the math students in that department to go out and be involved into these research experiences that normally we from what I've experienced here, normally we don't hear about all too often sometimes. And I'm grateful to be able, I was able to do these research experiences, such as the Math Spiral program in 2012. And I did research under Dr. Leon Woodson and path counting. And my junior year, I was able to do some more math biology at the National Mathematical Institute for Mathematical and Biology Synthesis, um, at the University of Tennessee at Knoxville. And additionally, my last 2 years at Morehouse, I was funded by the NIH under the Mark U. Star program, the Maximizing Access for Research for Undergraduate Students um, program, where I did research with Dr. Shelby Wilson in the math department at the time, in math biology, where we studied evolutionary dynamics of um, HIV and HIV and AIDS. So those trends with those programs, those REUs, and the support from the math department really invigorated me to be able to apply myself to go to grad school and see myself as a doctor, as a PhD. So going to graduating from Morehouse and transitioning to the University of Texas at Arlington. Um, so at the University of Texas Arlington, I got my PhD in mathematics, and under the prestigious under the chair of the department, my advisor was the chair of the department, Dr. Janlin Su, and during my time here, I've encountered many types of opportunities, the research collaborative research, and other things. And some of the few things that I've done here include being part of of a program called the Esteem Builders, which my academic sister actually created this LLC in order to bring more elementary and high school students into the realm of science and stuff. And I was one of their teachers. Additionally, I would come back to Nimbus for some some summer programs where we had intensive lectures and learned lot more about mathology and how we incorporate machine learning into those applicable fields. Additionally, one of my proudest moments here is being one of the founders of an organization known as the College of Science Black Graduate Student Association, where I was the vice president at the time when we founded. And what made me really happy is that we got Program of the Year our second year in, as we created a conference in order to break and discuss the barriers that occur in STEM, and we wanted to show that there are minority students that are doing fascinating and great research in their respective discipline in STEM. And because of that, we won Program Organization of the Year. And I just love the attention we got for it. And I hope we inspired many people during that time, especially here at UTA. Now, so now, so transitioning on, I want to talk about this idea of magnetic resonance. So more than often, you've probably seen somebody you probably know or have had some injury of some sort that require you to get some type of scan. And with MRI, the idea of MRI, it exploits nuclear magnetic resonance rather than using radiation that's involved in CT scans and X-rays in order to produce an image. Now, this machine, this is the machine that we use the machine that's used to produce this image is also known as the MRI machine, which throws magnetic waves in order to produce an image for the body part of interest. In this case, well, we expect that we were able to get a clear picture of the body of interest. But this is not always the case due to the fact of long data acquisition timing, which is very cumbersome to a lot of patients, especially those patients who are definitely have severe injuries and they can't stay still for very long. Or maybe you have a very wild child that just likes who can't just sit still for 15 30 minutes. Honestly, I couldn't do it. I wouldn't be able to sit still that long either. And what instead of having the image that we produce, instead we get something like this. Instead we get something like this, where we lose detail, and this detail that we have, the detail of the body structure that we had is no longer visible. Of the body, the body of the body part of interest is no longer uh, detailed, and it's a lot of degradation, and it's very detrimental to the medical application, especially when we're trying to diagnose and trying to give proper treatment to said injury, right? So what I wanted to do was try to solve this problem by speeding up the data acquisition process. If we can speed up the data acquisition process, we can avoid potential motion from the patient, even voluntarily or involuntarily. Though there may still have some type of dispute in blurring, and also, we also wanted to solve the fact, we also wanted to also deblur any foreign artifacts that occur in those scans that we take apart, that the MRI machine takes part of. So before that, I want to talk about what is an image per se, before I get into my algorithm and how we applied it to some MRI scan. So in image processing and imaging in general, a grayscale image is basically an array of pixel values that are structured such that we get the scene of interest or the view of interest, and each of these pixels have some type of value ranging from 0 to 255, where 0 represents black, and getting closer to 255 is white. So a bright pixel in that case, and everything between some form of grayish area. Um, Now, with those and how and they're structured in a way so we can get a some visible scenery that we want. And in this case, we have a 3x3. This is a 3x3 image that I produce in MATLAB, just to get an idea what these pixels are, what an image is on a smaller scale. But one of the issues when we're dealing with images is that we don't like dealing with high energy values. So what we do is we instead normalize these values and and convert them to double point floating precision numbers. So instead of going from 0 to 255, we go from 0 to 1. And we can think about this image as some type of matrix, and this matrix whose entries are those pixel values instead, that range from 0 to 1, and each pixel, and at the pixel location in each pixel location is denoted by I sub j, where I is the row and j is the column. Now, we want before and I want to discuss now I want to discuss some of the problems with image processing and this idea of compressed sensing, and what we can do to um, speed up data acquisition process, um, and also get over the hardware limitations that we have. So in compressed sensing, you've probably encountered this type of warning before on your computer or on your phones or whatever, is that your computer memory is very low, or you can't, you got to delete something, you don't want to delete it. And the issue in the issue there is that sometimes we don't want to do that. And the question is there a way that we can press those images or those messages in such a way that it doesn't take up so much space? And MRI, this is very important. This is very important, as I said before, that due to the fact that we have a lot of motion, a lot of movement going on with patients, whether it be voluntarily or involuntarily, we may have to do those retake a scan, do more scanning. We have to redo the scan, and with that in mind, we take up more space into those systems. So instead, compressed sensing will allow us to actually um, rather than taking the data set in full, let's just take a subsample and see if we can recover the image or the signal of interest with subsample and highly compressed data, highly compressed data. So in the traditional sense, the traditional sampling schemes go like this. So we have a very famous and very well-known picture that's used in a lot of image processing application, known as the cameraman picture. And what typically happens in the traditional sense for compression and reconstruction is that what we do is we take the cameraman's picture, we take the picture and we take it into some bases. In this case, we take the cameraman's been taken into the frequency domain or the Fourier domain, and from that space, we knock out some of those frequency values, which is in the third picture here. And what we do is we do an inverse Fourier transform, and we get the image back, telling us that we only need high frequencies, which tells us only a relatively few frequency values are needed in order to produce a fair representation of the image of interest. In this case, but even to that though, we do lose some type of detail, but also there is some noise that's associated with this as well, and we get a fair representation, but with sacrifice as well. So, and one of the problems with this is that we typically don't know where those important and high frequency values are located as a priori. And we're subjected to the Shannon-Nyquist theorem that basically tells us that if we want to get a fair reconstruction of our image from compressed measurements, we must sample at a rate that's twice the maximum frequency value present into our signal of interest. What compressed sensing tells us instead was we don't need to do this. Instead, as long we can get a nice representation of our image, as long as we meet these two criteria. The two criteria being that the signal of interest or the image of interest must be sparse in its natural domain, or it must be sparse in another must have a sparse representation in another domain, such as the wavelet, curvelet, and Fourier domain. And as well as the sampling scheme that we use must be incoherent, non-uniform sampling, random sampling, basically. And it has many applications in image processing, and what we'll use later on for magnetic resonance spectroscopy, which is basically an extension to magnetic resonance, which allows us to talk about chemical compounds and inhomogeneity inside those body parts of interest, and as well as SAR imaging and network tomography. Okay, so the presence of noise that's always in these systems, our image is not completely sparse, but it's almost sparse. And but even to that, that's good enough for us. So if we look at the cameraman picture, what I've done here is take the cameraman, took its Fourier transform, and sorted the coefficients by magnitude and I sorted the magnitudes of those coefficients in a decaying rate in a decaying order. And as you can see, most of those coefficients and most of those frequency values are relatively small. and we can still reconstruct our image using all nearly sparse coefficients in the frequency domain. And typically, this compressed sensing model can be given by this system y equals ax plus e, and the goal here is to be able to recover our sparse signal from our signal x from compressed measurements y. And there's been many types of algorithms that have used to solve this problem, such as the L1 magic, which is a cluster of algorithms in order to recover an image or a signal of interest, basis pursuit denoising, total variation regularization, so on and so forth. Now, so this is the first part of. So I just gave you just a brief background idea of what compressed sensing is. And I want to go to the second part, which is image blurring, and what does it mean to have an image that's being blurred. So image blurring, we've all encountered a problem like this, where we wanted to capture a scene of some sort, and sometimes the picture quality that we take, we end up having some type of degradation of our image, which we also known as a blur, occur, and we have to retake those pictures. For example, in this picture is when I graduated from Morehouse. And what I've done, and from the left is the original image, and the two on the right, the first image on the right is, well, in the middle, it's been blurred by some motion, right? So maybe you have a shaky hand, you're taking a picture, your hand shakes, and when you take the picture, you end up with a result like this. Or you can have motion blur occur when an object in the background is moving too fast, or whatever, you're panning too fast. And another type of blur is when the focus is the camera aperture is out of focus, and we result into another blurry type of image, and we don't like that. And so the question is, can we recover this true image from those blurry measurements? Let's see. Well, so I want to talk a little bit about image blurring and how we can think about it. So we can think about a blurry image Z to be the convolution of a sharp image X, and with another small array, an array that's smaller or the same size as X, known as the point spread function. And what this point spread function does is, it'll take, when we look at a pixel in that image, the point spread function will smear the light intensity of that pixel to its surrounding neighbors. And if we were to, and those, and the contribution of the blurry representation, for example, X1, is dependent on its neighboring pixels, like X sub 1,2, X sub 2,1, and X sub 2,2, in order to produce its blurry representation as Z11 as well. So the contribution of the neighboring pixels with the point spread functions will produce the corresponding blurry pixel to the sharp pixel itself. And to get a better understanding of what this point spread function is, let's assume that we have an image that has one single bright pixel in it. Okay, one single bright pixel, and we call that the point source. What the point spread function is, it's going to take this pixel, and it's going to take the light intensity of this pixel and spread it across its neighboring pixel values. And this is the basic idea. And the thing about the point spread functions are they have some special properties that we will exploit in our algorithm. And that is well, one of the good things about this point spread function is that most point spread functions are they're spatially invariant, meaning that no matter where my pixel value is, the point spread function the shape of the point spread function is exactly the same. That is to say that if I move my pixel value and I move it to another location, it looks exactly, the point square function looks exactly the same, no matter what. And it's a localized phenomenon. So so it's localized to that region or whatever, or the radius of the point square function itself. And so that's one, so that's a nice property to have. And most often than not, our point square functions are spatially invariant. There are spatial variant point square functions, but more often than not, this property known as spatial invariance is apply it happens more often than not than the variant part. Okay. But as I stated before, is that each pixel value, each blurry representation of those pixel values is contributed by the sharp pixel value and its neighbors. Well, what happens at the edge though? What happens at the edge? What happens to those pixel values? And if the point square function's radius is far beyond the field of view in our captured scene. For example, if we have a pixel value that's lying on the edge where this red box the represents the field of view, and we have a pixel that's on the very edge of, or the very edge of the image itself. Well, what is its value? Well, we don't know what's happening on the outside of the field of view, that is the red box in this case. And so what is the value of its blurry representation? Well, in order to remedy this, we need to impose boundary conditions. And the reason why we need to impose boundary conditions, and it's mainly because we make it for deblurring process, for deblurring algorithms. If we don't impose those boundary conditions, we may end up with some an image deblurring that results into these black borders around the recovered image, and we don't like that, and because it's not a good representation of the image that we want. And so we impose these boundary conditions. So what we do is we assume what's going to happen on the outside of the field of view. So I'm going to go over two of the boundary conditions that we can impose. The first boundary condition that we can impose is that we can think about our image X being surrounded by the void. Everything is black outside the image. Everything, there's just dark pixel values. Uh, Something just popped up. We can think about the image being surrounded by the void, and there's just black around it. And then second type of boundary conditions, we can assume that we embed the image inside a bigger matrix whose entries are literally the image itself surrounding it itself. So it's their replica copies of themselves. So those are the periodic boundary conditions in image processing. And with this idea of imposing boundary conditions and spatial invariance, we're able to rewrite our blurred image as a convolution of the point square function, and our sharp image as a linear system, or in a matrix vector multiplication in this case. And what we end up forming is of special structure matrices known as BTTB matrices or BCCB matrices, which is short for block topolix and topolix block matrices, and the other one block circling with circling block matrices. And what we call these type of matrices that are associated with that point spread function, we're going to call it the convolution or the blurring matrix. And we can and again, the structure of this matrix of whatever it forms depends on the boundary conditions we impose onto that point spread function. Okay. And we can give a similar take on the model of the blurring process, almost a similar fashion with the compressed sensing model as this linear system, where there's always going to be noise inherited in the system, in the imaging system. And the goal here instead is to try to deblur image Z, try to recover X from the blurry image, the blurry observations Z itself. So of Z, which this has been solved with many other type of algorithms, such as using SVD, using the linear filter, using linear filtering, or instead of solving this in the linear sense, we go into the frequency domain and solve this instead. And we have other iterative methods such as Richardson-Lucy algorithms that have solved this problem as well. So the big question. So we have two big theories, and we want to collapse them together in order to do simultaneous recovery of an image. Use an image that's been blurred, and we want to recover the true image using compressed measurements. So the main question is coming, and the main question and the answer to that is compressive deconvolution. And the question is it possible to recover a nice approximation to the ground truth image using highly compressed and blurred observation methods while maintaining the meaning and granularity of that image itself? So that is to say, and for example, the cameraman, if we have a blurry cameraman, can we recover the sharp image from it? And yes, the answer is compressive deconvolution. So we're going to try to simultaneously solve this problem using using an alternating minimization scheme in order to solve this problem. And before I even talk about the algorithm that I've been working on, the question is, the next question is, are blurred images compressible? And good for us, they actually are. If we look at the blurry images sort of wave coefficients in this case, the frequency coefficients and magnitude, we can see that the blurred images sort of wave coefficients actually have a faster decay rate than the original images itself, and that's good for us. And we can now apply the idea of compressed sensing and deconvolution in order to recover our sharp image as best we can from those blurry compressed measurements itself. So what I worked on for my PhD was to create a new novel compressive deconvolution model, and where we're going to solve this optimization. We're going to solve an optimization problem solve an optimization problem through an alternating minimization scheme, which will be solving two unconstrained problems simultaneously back and forth. And the compressed sensing model can be given by the following, and we want to recover, again, X from compressed and blurry observation measurement Z. So here's what I proposed was, let's do a non-blind compressive deconvolution algorithm using this alternating minimization scheme that joins the L1 magic and Tikhonov regularizations in order to recover our sharp image from those blurry measurements Z. And I want to take note of the word non-blind. Non-blind. When we're talking about non-blind, what I mean by non-blind is that we know what the point spread function is rather than it being unknown. And if we don't know what the point spread function is that causes that blur, we call it a blind, in this case, compressive deconvolution method. And there you can categorize those two. You have two categories of deconvolution methods, which is blind and non-blind. And the application, and we're going to apply this method. We're going to minimize the total variation of Z subjected to this constraint, subjected to this constraint. And what we're going to do and how our algorithm works is that we're going to alternate with one algorithm, and then to solve for one variable. That is, we're going to first do compressed sensing on our blurry measurements, and then using the L1 magic by solving a series of minimization problems. And then we're going to try to deblur using least squares approximation with Tikhonov regularization in order to try to recover our sharp image as well. So the basic scheme is what we do is we're going to input our initial guess for both the blurry and our sharp image, and we're going to input into our algorithm, and we're going to fix one of the variables. In this case, we're going to fix, we fix K and we fix X in order to solve for the next, approximation for blurry image Z using compressed measurements. And then from there, we're going to solve a system. We're going to solve another system, um, solve a least squares approximation problem using Tikhonov regularization in order for for the image to be deblurred. And we regularize in order to make sure our image is not super smooth or under smooth, which can result into staticky images or too much smearing going on in our images. And once we hit a specific tolerance, once we hit the specific tolerance, which once the dual gap is underneath the specific tolerance, we want to output what we recovered from that. And what we're going to do is we're going to apply what we did was we applied this algorithm to an MRI data set of a slice of one slice of a brain. So, oh, so before I talk about before I show you the result, I want to tell you what were the metrics that we use to evaluate our reconstruction. The first metric that we use is the peak signal noise ratio, the PCNR, which basically tells us the ratio between the amount of pure signal and noise. So the higher the signal noise ratio is, the better the reconstruction we've had. But one of the problems is with the peak signal noise ratio, there's been often the case where we have an image that's recovered that has a lower PCNR value. It looks great, but then we have another image reconstructed used with a higher PCF, but the quality looks worse than the one with a lower PCNR. So to remedy that, one of the better things we use is the structural similarity index measurement, which accounts for a lot of biological factors in the human perception. And what we do, and the value of this ranges from 0 to 1 for grayscale images. And the closer the value to 1 is, the better reconstruction reproduced from our algorithm we get. So 0 being the reconstruction looks nothing like the true image or what we wanted to recover. And the ultimate metric that we want to use is the human perception. We ultimately get the final say in what is a good reconstruction. And so underneath here, I define what the PCNR is and how do we calculate it, which you can actually implement this fairly easily in MATLAB. There is a command for this, as well as this is how to compute the structural similarity index. And again, two identical images will have a maximum SM value of 1. So if our reconstruction is fair, then we're closer to 1 than anything. Okay. So the images that we use and want to reconstruct is this image of a brain slice, brain data set slice, and the slice of a brain data set. And what I did here was incorporate two types of blurs on it. So the first blur that I use, which is the middle one, is a Gaussian blur with standard deviation of size 17 by 17. And then I also incorporated one of the motion blur, which is very relatable into a lot, like I said from the beginning, is that we have a lot of motion based blurring that comes from MRI scans itself. So what I did here was I artificially created those blurs in MATLAB and tried to recover those. And the results are the following. So the first results is what we get for the image reconstruction of the brain on the Gaussian blur. It says motion blur, but this is the Gaussian blur. And based on our structural similarity index, we got that the value was 0.82, which is fair reconstruction. It's close enough to 1. However, there's still problems with contrast, and there's still a little bit of ridges going on with inside the interior of this image as well. And the PCNR value was 31.2, and we had a relatively short runtime of 60 seconds. And finally, I incorporated an emotion blur and tried to recover the true image from that motion blur. And going through our algorithm, we can see that, yeah, we did get a nicer reconstruction. We did get a nice fair reconstruction and deblurring. One of the problems is that we do see some smoothing going on, and some loss of detail still. And our structure similarity index gives us a value of 7.4 and a PCNR of 3.205, and the runtime was about 55 seconds. And but still, we get a nice little representation of what the image would have been given the blurry observation, the blurry compressed measurements that's given by the middle. So I want to end off by saying, we presented this new type of non-blind deconvolution, compressive deconvolution algorithm, and it's possible, and we were able to recover an image using low sample rates, as well as it has the potential to speed up the MRI data acquisition using undersampling rather than fully sampling the data itself. But one of the issues that occurs here is that we don't know, typically in MRI, we don't know exactly what the point spread function is. And most cases, it really is unknown, because the motion, it can come from different types of movements, such as you just moving around, or respiratory motion, that's under investigation. That's what we'll be investigating later on in my postdoc journey. So for future works, I want to be able to refine this method in order to do compressive deconvolution blindly, but also to reconstruct those images, those 2D images and 3D images as well. Secondly, I want to also incorporate machine learning for auto recognition for those unknown point spread functions, and be able to perform a compressive deconvolution for those 3 Tesla MRI machines for the shoulder muscle I will be doing this at UT Southwestern, that under the funding of the NSF Mathematical and Physical Science Ascending Postdoctoral Fellowship that I was recently awarded. And I'm open up for collaboration on any insight that anybody may have, or that might relate to your problems. And yeah, I hope to be able to work with the AUC Data Science Initiative to spread and make this more of a broad subject for people to get involved into this area. So yeah, if you want to be involved, let me know. And that's it. Thank you.
Thank you so much for that really engaging presentation. I'll ask the participants, if you have any questions, please put them in the Q&A chat bar. And I think Bettina Gardner, who's our administrative director, has some poll results from the poll that was presented to give us an idea of who's with us today at our seminar. Bettina Gardner?
Hi, good afternoon, and thank you all for joining us. So it looks like, well, we didn't get as many people participating this time, but we got about 45% of our audience. And out of that, it looks like we only have 1 enrolled student, but everyone else is graduated already or working professional. So that's great to have all of you here with us and engaging with the Atlanta University Center. And then, since we didn't have very many students, we had masters, and of course, everyone else, we had 2 master's students and everyone else were not currently enrolled. The split is about 1/3 female and 2/3 male. And then in terms of where everyone is located, It looks like 2/3 of our audience are outside of Georgia. So if you'd like to post where you are, your city and state or country, that would be great. But welcome everyone. And thank you once again for joining us.
All right, thank you so very much for that. That's great. So if we have any questions from the participants, those in the audience, please place them in the Q&A chat, and you can ask anything you'd like of our presenter. But I'll first start. So you talked about, you took an image and used MATLAB, which is great, and you blurred it and then see if you could reconstruct the original image. Are you also planning to extend that? How are you planning to extend that to, let's say, a real world scenario of somebody kind of moving around?
Right. So that's a good question. The thing is, like as I said before, there's with the deconvolution part, there are two types. There's two types: the non-blind, and then there's the blind deconvolution part. Now, the issue with my algorithm is strictly that it's non-blind. We know what that point spread function is. But instead, in a real case scenario, we typically don't know what that point spread function is. It's blind, right? So what we try to do is estimate what that point spread function is using various measurement tools. One way you can do it is thinking about it. In the slide presentation, I told you that you can, if you think about an image with 1 pixel value, right, with 1 pixel value and blur it, you can literally do a tedious task by just keep going column by column and blurring it and get an estimation of what that point spread function is. And so in actuality, we don't want to do that. That takes way too much time. So there are other ways to estimate those point spread functions, in which I'm under investigation with that right now too.
That sounds exciting. So you talked about how you wanted to expand this work and incorporate machine learning into it. How will that extend what you do? How will it add value to some of the techniques that you're developing?
Right. I think more so. It's going to be very beneficial to those medical applications, right? That's mainly because trying to estimate those, once you get the estimations for those point spread functions, what causes those blurs, once you get those right, you can create a dictionary in order to try to auto recognize exactly if a patient comes in and you have a kid, just let's say a kid, for example, who's very wild and very energetic. He doesn't want to move. He or she doesn't want to stop for, I don't know, 30 minutes, right? Once you have the dictionary, we could be able to speed up the process and no longer have to redo a scan, right? To redo those scans. And that's mainly because we have that dictionary, and also we're undersampling, right? We're undersampling. We no longer need the full data set in order to reconstruct the said MRI image itself.
So how, I think in the long term, this then could actually be used in the health industry to get better images. Do you foresee it as being incorporated in the technology that's being used? Or how do you see this being implemented, let's say in the day-to-day uses at a hospital, for example?
I believe this can be very much so used into those medical applications, especially when we're talking about cost and money, cost and time, right? So if we're able to speed up the process, we're spending less money, more, the quicker we can get a scan done, the less we need to actually produce, the less we need to pay for in order to, do those scans and stuff. And eventually, maybe far in the future, you might be able to do your own MRI scan, right? But that's far, and we're not that far yet with that. So I see it in those medical applications, especially when we're talking about time. and money, right? The money side is more for the medical application, trying to buy those machines, those big powerful machines. The other side is the patient, who also needs to pay, but also it's a lot of time to spend, right? You have to go out of your way to get an MRI scan, right? And like I said before, it's that with that uncumbersomeness and those beds, those MRI machine beds, you may not want to lay on there for too long. You may not want to lay on there too long. Yeah. So yeah, that's my
It's good. You know, it may come faster than we know, right?
right.
Right, yeah. So somebody has a question. They ask, did you have any computational issues while reconstructing?
There's always an issue with the computational part. And one of the big issues is mainly what was the initial what do you initially guess, right? That's one of the things in a lot of algorithms. How do you initially, what do you take as an initial guess? Maybe you can only use a certain type of initial guess to start your algorithm. In this case, we had a few initial guesses, but but ultimately only two actually worked, and that's a subset of infinitely many type of initial guesses you can have. And that's one of the big issues in when you're computing algorithms. I think that's always the first thing, is just figuring out the initial guess. The second thing was incorporating these two minimization schemes in general, right? I have one minimization scheme that's solving for compressed sensing. The other one is doing the deblurring part. And you ultimately want to make sure that the estimate that you get is you want to get the estimate that you want to be under some tolerance or some epsilon or whatever. And that was a big issue. And we wanted to make sure that our method actually converged. The good thing about our method is that when we recast the method it's a bunch of minimization problems. And what happens is we convert our constrained problem into an unconstrained problem, in which when we convert it to an unconstrained problem, it ends by recasting it into a second order cone problem, our problem becomes convex. And with that convexity, we guarantee that our method converges. So
That's interesting. Yeah. So it's an iterative process that's bound in a domain. So you know it's going to go to something, right? Yeah. So going back to that initial guess. Yeah. So the person has the same question I do. I'm going to read hers though, or his. Yeah, read their question. Is your algorithm sensitive to initial guess? And then why is it sensitive to the initial guess? And then, is your problem nonlinear?
Right. So the problem is it's hard for me to give a concrete answer for the initial guess, but yeah, it is very sensitive to those initial guess. That's a great question. That's a very good question. It's sensitive to those initial guess, and that's due to the fact that due to the fact with the mostly for the L1 magic, because that's sensitive. That algorithm already is sensitive to initial guesses itself. I forgot what the latter question. What was the latter question?
So is it sensitive to the initial guess that if you don't pick it in such a region, you're not going to converge onto what it would just fall outside. So it sounds like there's some sort of
you need to be in a feasible region.
Right? So it's like going back to Newton's method or something like that, right? You're not going to converge to something if you're outside of that feasible region. And then so are you thinking about maybe you talked about having like a dictionary of images that you could, depending on computational speed and power, the dictionary of all these images, you could kind of bootstrap over a initial guess to kind of figure out which one's the best initial guess. So, or have you thought about ways in which to refine the methodology or the technique for getting that initial guess so that you're actually in that region for a given image?
I haven't really thought too much about it. I'm still looking into that and reading more articles and papers and what they've done, what other people have done, especially when this area is relatively new. Because you're talking about I like to say super ill-posed problem, because you're combining two ill-posed problems in general to one super one. And so I'm still reading upon that and seeing better ways to get a feasible and initial guess. That's my answer to that.
Yeah. So the second part of the question is your problem nonlinear?
Yeah, with the inherent noise of images, yes, definitely is.
Yeah, because there's a lot going on. And even with these iterative processes, right? So like you said, it's going to be some sort of feasible region. And in my mind, if you have some sort of body part, you know, maybe there's in my mind, I'm thinking there's a feasible region of spaces that the body part could be or look similar to as the initial start, if there's like a dictionary of images, and then try to optimize and figure out which one it is to, maybe you'll get convergence. That would take a lot of computational power. I recognize that because it's on two ends. So the person says, is the operator that you're working with, is the operator nonlinear?
Well, there's two operators, right? There's the convolution operator and there's the sparsifying operator. The sparsifying operator is definitely nonlinear. The convolution operator, on the other hand, the convolution operator, yeah, that the way I did it, yes, that is also nonlinear as well. So to answer that question.
Good. So it sounds like there's a lot of interesting work already underway, and it sounds like there's a lot more that could be done to really get these images properly, and then infusing machine learning into that and having these dictionaries of images that could bootstrap it up even further. So no, this is fascinating, really interesting. So with that, I know we're kind of at the top of the hour here. Thank you, Dr. Johnson, for coming back home to the AUC, Morehouse alum, class of 2016, and Spiral alum, class of 2013, right? Yeah, got to give the shout outs where you can. And so thank you, and we look forward to having you work with us when your postdoctoral work begins in January, and continuing this journey with you.
Thank you.
And thank you, everybody, for coming and for the great questions. So have a great day, everyone.